The Webb can see the formation of the first galaxies. It's essentially looking all the way back to very close to the beginning of time.
Scientists are getting their money's worth. They use the powerful $10 billion James Webb Space Telescope to peer into some of the deepest cosmos, and for the first time captured views of the earliest stages of the universe, gathering sharp, pristine, and beautiful insights of early star and galaxy formation, and providing insights into the formation of planetary systems, including our own solar system. But in some sense, James Webb was almost too good, far exceeding all hopes and expectations. Astronomers expected to find some of these infant galaxies with Webb, but they didn't expect to find so many. Webb's unprecedentedly deep views revealed a colossal surprise: a bunch of the impossible early galaxies. Even at these earliest times, these galaxies were too big, bright, and numerous to explain, some of which are even older than the universe. Our best cosmic predictions, based on lambda cold dark matter, the standard model of cosmology, didn't expect what James Webb saw. In other words, discoveries made by James Webb could shake their understanding of galactic history. So, is the Big Bang and all of modern cosmology in trouble? Join us as we dig deep into how James Webb just found massive structures that could defy our current theories of the universe. The farther and farther back into the distant universe we look, we have a picture of what we expect to see. At some point, we should find the first and earliest bright, large, luminous galaxy, and we should see their number density rapidly decrease as we approach that limit. Before that, we should find only smaller and less evolved galaxies, decreasing in number and number density until we find the very first among those. Before that, we should only see individual star clusters and proto-galaxies, and these should be extremely blue and primitive, and again should only exist in low number densities the farther back we go. And finally, there should truly be a time where the very first stars and star clusters of all appear, and beyond that, there should be no luminous sources at all to observe, excepting the Big Bang's leftover glow itself. When we look into these deep depths of the universe and examine these galaxies, we're basically asking the universe, how did you grow up and come to be the way you are today? Given that we have a model of the universe, a mix of dark matter, normal matter, dark energy, and a little bit of radiation, we can arrive at predictions for what we expect to see in the universe at any given time. Looking at these distant objects with the James Webb Space Telescope, and with its spectroscopic capabilities in particular, allows us to test that model and to see if we truly understand the universe we inhabit, or if, and how, we have to revise our picture of the cosmos. The James Webb Space Telescope is changing astronomy in many ways, from peering into the atmosphere of exoplanets to capturing stunning images of distant cosmic phenomena. But perhaps its greatest scientific contribution is its ability to observe galaxies that are so distant that looking at them is like looking back in time. Projects like Webb's JADES or the JWST Advanced Deep Extragalactic Survey Program are scanning the sky to pick out some of the oldest galaxies we've ever seen. When scientists first turned Webb toward apparently empty patches of sky to look for these distant galaxies, they found something very strange. They didn't just find a few very old galaxies, dating back as much to just a few 100 million years after the Big Bang. They found far more of these galaxies than anyone had predicted. One particular galaxy jumped out of the JADES data straight away. The record-breaking galaxy, named JADES GS Z14-0, appears to us as it existed 290 million years after the Big Bang, when the universe was a mere 2% of its present 13.8 billion year age. This places it well within a mysterious epoch called the Cosmic Dawn, when the universe's first stars began to shine and galaxies coalesced. The former record holder, a galaxy named JADES GS Z13-0, that was reported in 2022 by University of Arizona astronomer Kevin Hainline and his colleagues on the JAID's research team, was observed about 325 million years following the Big Bang. To be honest, this age difference may seem unremarkable. Cosmically speaking, not a lot usually happens in just 35 million years. But JAID's GS-Z14-0 has properties that are vastly different from its slightly older counterpart, making it an anomaly that has experts second-guessing how the universe's first galaxies evolved.
I was skeptical that it was anything special for a number of reasons. It just seemed too big and too bright. But in January of this year, when we confirmed that it is, in fact, the new record holder, I just laughed. I had to get up from my office chair and walk down the hallway and look at the faces of the other JAID scientists.
The group's initial doubts were well-founded, says Brant Robertson, an astronomer and JDS member at the University of California, Santa Cruz, who is also a co-author of the preprint paper that reported the new record holder. James Webb has been unveiling candidate early galaxies that seem to shatter experts' expectations since it began operating in early 2022, but some of them were ultimately proved to be imposters, more modern galaxies much closer to us in the universe than Webb's first glance would suggest. Unsurprisingly, the farthest galaxies are the hardest to accurately observe and verify. Their qualities can be the most fascinating yet deserve the most skepticism. And JAID's GS-Z14-0 was no exception to this rule. At first, scientists thought it was just one half of another galaxy. With closer examination, they found that to be illusory. The other galaxy was a foreground object, an entirely different system billions of light-years closer to us that just happened to overlap with JAID's GS-Z14-0 in our line of sight. With that relationship untangled, the candidate's bizarre qualities became clearer. If it was an early galaxy, JAID's GS-Z14 was abnormally large and unusually shaped.
At that point, I had been looking at thousands of little smudgy galaxies. But then this one came along, and I sent it first to my colleague Jake Helton of the University of Arizona and said, "This is seriously weird." And after looking into it more for some time, I knew we had to get a spectrum on it.
Generated by an instrument called a spectrograph, a spectrum serves as a sort of cosmic barcode, an image of light split into all of its various wavelengths or colors that scientists can study to reveal otherwise hidden details, such as an object's distance from Earth. James Webb has a spectrograph that takes the light from these distant galaxies and disperses it like a prism does into its component wavelengths to make a rainbow, basically. Based on the features of that rainbow, scientists can tell how far away a galaxy is. It's pretty much how they always confirm the distance of any faraway system. Scientists use the spectrum of a galaxy to then calculate its cosmological redshift, a numerical value that represents the stretching of light from shorter, bluer wavelengths to longer, redder ones that is caused by the expansion of space itself between a light source and an observer. The farther away an object is, the faster it is receding because of cosmic expansion, and the higher its redshift becomes. Every celestial object visible to the naked eye is too close to exhibit this effect and thus has a redshift of 0. A redshift of 1 corresponds to a distance of more than 10 billion light-years. JWST's studies showed that JAID's GS-Z14-0 has a redshift of 14.32, the highest ever recorded. For comparison, JAID's GS-Z13-0 has a redshift of 13.2. But this new galaxy's superlative redshift isn't what makes it so intriguing. In fact, the JAID's team suspects several other candidates awaiting confirmation may have higher redshifts and be from even earlier points in the universe's timeline. Instead, what makes JAID's GS-Z14-0 so peculiar is its exceptional brightness, size, and color, all of which seem linked to its population of stars. Most known early galaxies are relatively small and dim compared to modern ones, mostly because their relative youth hasn't afforded them enough time to grow large and laden with stars. Jadis Geese is 14A seems to be an outlier, appearing as an especially radiant blob that suggests it's packing hundreds of millions of times the mass of our Sun into a diameter of approximately 1/700 light years. For comparison, the diameter of JD's GS Z13-0 for comparison is nearly 10 times smaller. Some theories might allude that such brightness comes from a burgeoning supermassive black hole feasting on gas at the center of JD's GS Z14-0. But in that case, light is usually concentrated into a much smaller region. Instead, the best explanation Heinlein and colleagues have found is that this exceedingly young galaxy has somehow already manufactured about 500 million stars. However, the galaxy's true stellar productivity may be even greater, based on its strange color. Typical growing galaxies produce both high-mass stars, which shine bright and blue for circa 10 million years before dying, stars which shine redder and fainter for hundreds of millions to billions of years. Young galaxies, then, are usually very blue, because most of their bright, high-mass stars have yet to burn out. But JD's GS Z14-0 isn't very blue. It's actually pretty red. Stardust may have something to do with this. Anyway, dust is usually created when stars expel their matter or die. Galactic dust causes light shining through it to appear red. We see this clearly down here on Earth when dust in our atmosphere turns sunsets red and orange. Another sign that stardust may be the culprit is the galaxy's mid-infrared glow measured by James Webb, a clue that Jade's GS Z14-0 is populated with clouds of ionized oxygen, an element forged in the hearts of stars. If dust from dead stars is the explanation, though, it raises a more perplexing question. How could a galaxy so young have already sparked so many stellar generations? Either way, usually gases like oxygen show up only after large groups of stars have lived their lives and died in supernova explosions. So, seeing oxygen in a galaxy this young is like if you are an anthropologist and you find an enormous ancient city that has evidence of iPhones. In short, Jadis GS Z14-0 poses all kinds of new questions and theories. But this galaxy is not the only universe breaker. Under James Webb's views, some of the early galaxies look a lot like galaxies in the local universe. They seem to have added structure and maybe even spiral arms. That wasn't something we really expected. The high level of structure and brightness in these galaxies is leading some astrophysicists to question the age of the universe. In an attempt to explain the impossible massive galaxies existing so early in the timeline of the universe, a researcher has posited that the universe is roughly twice as old as previously believed. They push the age of the universe from a spry 13.8 billion years old to roughly 26.7 billion years old. That's an interesting scenario, but it doesn't correspond to the evidences at hand. So, up to now, there's currently no consensus on what is the root of the discrepancy between the models we have and the data we observe with Webb. The answer could be related to dark matter and its role in the early universe, or it could be that the way early galaxies were formed was spurred on by forces that haven't been considered yet. However, it's worth noting that even before the James Webb Space Telescope, scientists knew that the early universe was a very different place from the universe today. Its galaxies were made almost entirely of hydrogen and helium, were shaped by tendrils of dark matter, and hosted enormous bright stars that lived fast and died young. While the laws of physics haven't changed over the past billions of years, the scale of the universe has, and that affects how those physical laws apply to galaxies. When the universe was smaller and denser, that affected the ways in which stars form in complex ways. Another way in which the early universe was fundamentally different is in its overall chemical composition. Heavy elements like metals were almost entirely absent in the early universe because these elements were primarily formed within stars and spread by their explosive deaths, called supernovae. It took several generations of stars to spread these heavier elements through the universe and to be absorbed into stars similar to those we see today. The hypothetical earliest stars in existence are referred to as population 3 stars. Today's young stars are population 1 stars, and the numbering counts backward in age. They were much bigger, heavier, and bluer than stars today, and they gave off more ionizing radiation. Those differences are because of the way stars generate heat and light in a process called fusion. If a star is made only of hydrogen and helium, to do fusion the star has to be hotter and denser than a star that has carbon, nitrogen, oxygen. There's a different chemical pathway to create fusion, and that requires a larger size and more mass to support it. No one has ever observed a population 3 star before, and finding one is one of the holy grails of modern astronomy. But scientists believe it could be possible to find one using Webb. Anyway, James Webb was built primarily to transform our understanding of the early universe. And telltale evidence gathered by the James Webb Space Telescope suggests we're closer than ever before to finding elusive first stars of the universe. All of this discussion of billion-year-old history might seem rather abstract, but in fact, it's directly relevant to understanding the universe as we see it today, and as the James Webb Space Telescope is revealing in greater detail than ever before. That's because astronomy operates on such long time scales that we can't watch objects like galaxies across their lifespans. Most galaxies we see around us today look like the Milky Way, but we can't see them develop over time. To study that development, we need to look for distant and ancient galaxies, which some scientists refer to as baby pictures of the Milky Way. It sounds cliché, but before we can understand where we are and where we're going, we need to understand where we came from. A piece of good news, most recently, we have just taken our first steps into the hunt for dark matter, the most cryptic material in the universe. The Hubble Space Telescope has shown that dark matter is concentrated within the core of a nearby dwarf galaxy, a finding that rushes to the rescue of the standard model of cosmology. This model basically predicts dark matter to be cold, but recent findings have started to hint at the substance being warm. However, these new observations are on the standard model's side. Dark matter is the invisible substance purported to make up 85% of the mass of the universe, but nobody knows what dark matter actually is or exactly how it behaves. Our best idea is that it is cold, which, in other words, means it is predicted to consist of a low-energy particle that's not zipping about hither and thither, but is rather slow-moving and capable of clumping together to form huge halos inside which galaxies grow. The concept of cold, dark matter and its influence on structure formation in the universe is a critical part of our current standard model of cosmology. That part is known as lambda cold dark matter, or LCDM model. In the cold dark matter paradigm, dark matter should especially pile up in the core of a dark matter halo. Hence, dark matter should be densest in the core of a galaxy that grows inside that halo. Astronomers call this the dark matter cusp because of the shape it makes on a graph of dark matter density relative to its radius from the center of a galaxy. However, astronomers have been stumped by some recent observations of dwarf galaxies that have hinted that dark matter might behave differently than they thought. Instead of acting like cold dark matter and clumping most densely in the core of the dark matter halo, these observations imply that dark matter may be more evenly distributed throughout a galaxy instead. This would be a sign that dark matter is warm or have enough energy to not clump together so much. If true, this would have significant repercussions for our cosmological models that rely on dark matter being able to clump in certain ways. Now, astronomers led by Eduardo Vitral of the Space Telescope Science Institute in Baltimore, Maryland, have put this to the test. Dwarf galaxies are the best place to study dark matter because, proportionally, they have the highest abundance of dark matter of any galaxy type. The Draco Dwarf Galaxy, which was chosen for this study, orbits our Milky Way galaxy at a distance of 250,000 light-years from Earth. In Hubble's archives, there is data describing the motions of stars in the Draco Dwarf spanning 18 years, between 2004 and 2022. Vitral's team were able to use these motions to calculate an accurate measurement of the Draco Dwarf's gravitational field, and hence the distribution of its mass, including the part dedicated to dark matter. By combining the proper motions of the stars, that is, their motion across the sky, with their radial motions toward or away from us that is detectable as either a blue shift or a red shift in light, Vitral's team was able to track the movements of the stars in the Draco Dwarf in 3D. As team member Sangmo Tony Sohn of the Space Telescope Science Institute in a statement, "When measuring proper motions, you note the position of a star at one epoch and then many years later measure the position of that same star. You measure the displacement to determine how much it moved. For this kind of observation, the longer you wait, the better you can measure the stars shifting." Certainly, Hubble's longevity in space is an advantage here, as is its powerful resolution from its vantage point high above Earth's turbulent atmosphere. The proper motion of the Draco Dwarf's stars over the course of 18 years at a distance of 250,000 light-years is tiny, equivalent to less than the width of a golf ball on the moon as seen from Earth. Hubble's results are therefore the most detailed measurements of stellar motions in another galaxy ever made. Using these stellar motions, Vitral's team was able to conclude that the total mass of the Draco Dwarf's dark matter halo, out to a radius of nearly 3,000 light-years, is 120 million times the mass of our Sun. Furthermore, the results strongly indicate that the Draco Dwarf's dark matter density profile does have a cusp in the core, and that therefore dark matter is probably cold. As the researchers write in their research paper, the results lessen the tension around the cusp core problem and give further credence to standard LCDM cosmology. Our models tend to agree more with a cusp-like structure, which aligns with cosmological models. While we cannot definitively say all galaxies contain a cusp-like dark matter distribution, it's exciting to have such well-measured data that surpasses anything we've had before. Therefore, the next step is to repeat the analysis for other dwarf galaxies, and Vitral's team are currently working on studies of the Sculptor and Ursa Minor dwarf galaxies, which also orbit our Milky Way galaxy. If the findings can be repeated in those and other galaxies, it would effectively rule out some dark matter candidates, such as sterile neutrinos and gravitinos, the latter being a hypothetical particle predicted by the theory of supersymmetry as being the massive partner to the equally hypothetical but probably real graviton. The results therefore strengthen the possible models of cold dark matter, principally weakly interacting massive particles or WIMPs, primordial black holes and axions. Meanwhile, elsewhere on Earth, scientists have used supercomputers to create a synthetic universe that will help predict what the next generation of super telescopes will see upon opening their eyes to the cosmos. These telescopes will both be dark universe detectives in that they will investigate the two most pressing mysteries in cosmology, dark energy and dark matter, sometimes referred to collectively as the dark universe. Notably, the news comes as the $10 billion James Webb Space Telescope celebrates 2 years of delivering scientific results. The Webb telescope has had an immense impact on astronomy, with researchers still working to understand some of the surprising things it has seen. The newly generated synthetic cosmos should help scientists avoid at least some of the same elements of surprise when both NASA's Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory start exploring the universe, though these telescopes will undoubtedly still reveal some unexpected delights of their own. This simulated universe was created with the Theta supercomputer at the Argonne National Laboratory in Illinois as part of a wider project called Open Universe. The copycat cosmos consists of nearly 4 million simulated images depicting the universe as it should appear to Roman, set to launch in 2027, and the Earth-based Rubin currently under construction at the peak of Cerro Pachon, a mountain in northern Chile. In the words of Katrin Heitmann, Deputy Director of Argonne's High Energy Physics Division, who managed the project's supercomputer time, using Argonne's now-retired Theta machine, we accomplished in about 9 days what would have taken around 300 years on your laptop. The results will shape Roman and Rubin's future attempts to illuminate dark matter and dark energy, while offering other scientists a preview of the types of things they'll be able to explore using data from the telescopes. Despite being very different observatories, Roman, located around 1,000,000 miles from Earth, and Rubin, located at high altitudes in the dry and clear atmosphere of northern Chile, will both investigate the mystery of dark energy. Dark energy is a placeholder name for the mysterious force driving the ever-accelerating expansion of the cosmos. The nature of such expansion remains a mystery itself. This substance has proven troubling for scientists because dark energy dominates the universe, accounting for around 68% to 70% of the total matter-energy budget of the cosmos. The open universe simulation could help scientists better understand the signatures of dark energy they will see when Roman and Rubin start delivering images. This could mean that even faint fingerprints of dark energy could yield important scientific results right out of the gate. Ask Jim Chiang, a scientist at the National Accelerator Laboratory who helped create the simulations, said in the statement, "Open universe lets us calibrate our expectations of what we can discover with these telescopes. It gives us a chance to exercise our processing pipelines, better understand our analysis codes, and accurately interpret the results so we can prepare to use the real data right away once it starts coming in." Roman and Rubin will also be influential in understanding dark matter, which accounts for around 26% of the remaining matter and energy in the cosmos. This mission will be particularly poetic for Rubin because it is named for Vera Rubin, the American astronomer who established the presence of dark matter in galaxies. Dark matter, as told, is problematic because it does not interact with light nor ordinary matter. Or if it does, these interactions are so weak and rare we can't detect them. This means dark matter can't be composed of electrons, protons, and neutrons, like everyday matter is. That's because everyday matter certainly interacts with light and with itself. Astronomers can only infer the presence of dark matter from its interaction with gravity, which in turn influences everyday matter and the passage of light. Rubin and Roman, named after Nancy Grace Roman, NASA's first head of science, affectionately known as the Mother of Hubble, and who pushed for powerful space telescopes to be built in the first place, will hunt for these effects. This dark universe investigation, set to be undertaken by Rubin and Roman, will be no mean feat. Rubin, set to begin operating in 2025, will rely on the largest digital camera ever built to investigate the dark universe, while Roman will offer a much wider view of the cosmos than the Hubble Space Telescope or the James Webb Telescope can. In fact, even simulating what these telescopes would see was a complicated task requiring a huge amount of computing power. Now that it is done, however, the Open Universe team is confident the benefits will soon be self-evident. As Kiesling concluded, "We made phenomenal strides in simplifying these pipelines and making them usable. Now we want people to start working with the simulations, to see what improvements we can make and prepare to use the future data as effectively as possible." Notably, beside using telescopes and supercomputers, scientists also hunt dark matter in experiment lab. Early this year, an experiment designed to search the cosmos for its most mysterious stuff, dark matter, has delivered its first results. While the broadband reflector experiment for axion detection, BRED, developed by the University of Chicago and the U.S. Department of Energy's Fermilab, hasn't turned up dark matter particles just yet. The new results place a tighter constraint on the type of characteristics scientists can expect such particles to have. The BRED experiment itself also served up an exciting new recipe that could be used in the hunt for dark matter. a relatively inexpensive one that doesn't take up a vast amount of space. Bread takes a broadband approach to search for hypothetical dark matter particles called axions and associated dark photons across a larger set of possibilities than other experiments, albeit with slightly less precision. As University of Chicago scientist and Bread project co-leader David Miller said in a statement, "If you think about it like a radio, the search for dark matter is like tuning the dial to search for one particular radio station, except there are a million frequencies to check through. Our method is like doing a scan of 100,000 radio stations, rather than a few very thoroughly." The proto-bread experiment ran at the University of Chicago for a month and delivered some interesting data, whetting the team's appetite for the full-scale experiment. The test results showed that bread was highly sensitive in the range of frequencies that the team had designed it to probe. "This is just the first step in a series of exciting experiments we are planning," Bread co-leader and Fermilab researcher Andrew Sonnenschein said. "We have many ideas for improving the sensitivity of our axion search." The test also demonstrated that particle physics can be done on a tabletop as well as in huge particle accelerators like the Large Hadron Collider, which runs for 17 miles, or 27 kilometers, deep under the border between France and Switzerland. According to Stefan Knirk, the Fermilab postdoctoral scholar who led the development and construction of bread, this result is a milestone for our concept, demonstrating for the first time the power of our approach. It is great to do this kind of creative tabletop-scale science, where a small team can do everything from building the experiment to data analysis, but still have a great impact on modern particle physics. The next stage of the bread experiment will see the apparatus transported to the magnet facility at Argonne National Laboratory. Additionally, facilities like SLAC National Accelerator Laboratory, MIT Caltech, and NASA's Jet Propulsion Laboratory are working on research and development with the University of Chicago and Fermilab for future recipes of the bread experiment. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.